I'm Guo Cheng Guang, 12 years old, primary 6. Right now here, at ordinary differential equations, we are still revising of our methods, our different types of ordinary differential equations. In the last lesson, we have revised about the Wronskian determinant, and which we use it for determining whether the solutions to an ordinary differential equation that is homogeneous, whether these solutions are linearly independent. And linearly independent, it means each of these solutions, they cannot undergo an operation then gets another of these solutions. So right now here, we're going to say about something about the Bernoulli equations, but we'll combine it with physics. Okay, in physics, there is this F equals ma. Okay, F equals ma is the Newton's law of motion. So F equals ma. This part, F, you can say that is the resultant force. You can say it is the net force. M, it is the mass, but it is the mass of this inertia. A is for the acceleration. Another way we can write this, acceleration, it is dv dt. V is velocity, t is the time. Next we can write this, d square x dt squared. So x right now here is just that distance. Okay, although we do have these ways of writing, but you still can write it as, for example, this dv dt. You can write it as v, then there's a dot above. Or if you want to write this x, it can be x with two dots above. These are ways to write it. But if you write this with a dot, it is always with respect to t. Okay, so this always with respect to t. But are there any other ways of writing this? For example, if we don't know what this m is, this f, there's some relationship with v, with this dot above. There's some sort of relationship between them. So this relationship we might not know, but we can express it using the proportionality. So we can write it as f, it is proportional to this differentiation of v. But for these parts, what if there is this square? What if there is this cube, or even square roots, cubic roots, all those different types, and so on. There are many different types that you can write it. And if you want to write it, for example, this first example here, you might just write it in this form, or you might write it in this form. But what if we actually don't have this dot above? If you don't have this dot above, it becomes like this. But there are such things. There are such things. So that means when you write it out in this, you can say it like equation form. Then you can say where you'll most probably find this. Well, this you'll most probably find it in fluid dynamics for this part. But wait, is there some sort of mistake in here? Is there? Let's see. What if we think about units? Is there anything wrong with these units? V, velocity. Okay, so we just need to find out whether this k has that right unit. Then for this Newton here, which is this M, there's still the kg, because this mass is usually used for kg. Okay, this part for the N is according to here, F, using this part. M. Okay, so that means this is just kg per second. So if this k is kg per second, that is right. So if the unit of this k is kg per second, then it's alright. But there is still something wrong going on here. Let's think again. This resultant force, K and V. Let's just say you walk in this direction. Then you have that force acting on you. But this force, like if you're moving in the air, then this force will be air resistance. So that means air resistance is acting in the opposite direction. Opposite direction, that means you need to have a negative. Well, this negative, it doesn't actually mean a negative force, but it's just the direction of this. So that means we need to write it as F, that is equal to a negative kV. But then what do we think of again? This might be one of the ways. This is just at this velocity. What if we have many of these? And so on. What if we do have many of these? For example, I think I can fit one more here. Okay. But do you find that this is still some sort of thing in here? Let's see about this. F, and you have inside K1V, this negative K1V, then a negative K2V square, then a negative K3V cube, all these, so on. How about thinking of the graphs? For example, this square. Okay, if you have V square, this graph is like this. How about V cube? Let's see about this. V cube will be like this. What's so different about them? If this square or just any even powers, that means y, you only have this positive part. But if these are odd, then y, you can have positive part, you can have negative part. So, can we call it like even function and odd function? Well, yes, we do have that. This part with all the even powers are actually even functions. So that is f, if yours of a negative x, but it is still equal to fx. It is symmetric about this y-axis. How about for these odd functions? Odd functions, are they somehow symmetrical? Well, actually they're symmetrical about this origin. This origin. Here also have origin. So this is symmetrical about origin. What if it is f negative x, negative what will this be equal to? You get a negative x here, but this is symmetrical about this origin, so it is actually equal to negative fx, symmetrical like this. So, but what if we want to take out something from it? If we want to take out something from it or negatives from this, but this is only for positive part. If it is only for positive part, but then we want a negative part, so that means these parts cannot. But for these parts in this only thing, it cannot. So that means you get it like this. Okay, so all that's left will be these with the odd power. For this part, it is actually only for positive v. So what if we do have this negative v? So that means all these are going to become positive. Okay, all these are positive. Then what if we just change this v for y? By this part you might think, wait, how about those squares power 4s? In the Bernoulli equation, didn't we have those? Well, actually in these, we can have them, but right now here, we're only considering about resistance. Those with square power 4, they have external forces, and we'll discuss about that in future lessons. For this equation, you might write it like this, but in the case we are having right now here is without this part. So that means just like this. It is until first order. Oh, this is just one of them. How about all the other cases? All those other different cases. So let's just say, for example, this f equals m8, which are actually all in vectors. This f, resultant force, there are different forces and they might be acting from different directions. So different forces, that means they'll have different accelerations, can be from different directions. Then what if we add all these forces together? So this part m, as they are all acting on this same mass, so that means these accelerations can also put together. So at this part, they can be added together. Then you get all these resultant force and this resultant acceleration. So at this part, all these can be added together. So it's something what we call the superposition. Wait, in the last lesson, we have shown the Wronskian determinant. We have revised about that. So the Wronskian determinant about linear independence, I think can be used here actually. So all these things are actually linked together and you can use them together in different cases. So this superposition case will be the same in this Bernoulli equations. Okay, so I hope that you're all clear so far. So thank you for your watching.